With the talk, dynamic data pricing, a mean field stackable game. Please, he is here.
Okay, thank you.
Okay.
Now, can you see my screen?
Yes.
Okay. Uh, Today I will give a presentation titled Dynamic Price Data Pricing, a Midfield Stack Board Game Approach. It's based on the joint work with Professor Li Junbo and Shihua Wang in Xidian University. In this presentation, we will explore a novel analytical framework that combines midfield games and stackable games to address the pricing problem in large-scale dynamic data markets. And my presentation will be structured into 5 parts. First, I will introduce the research background and motivation. And next, I will introduce a 3-tier game model proposed in the paper. And then we will discuss the methods used to solve this complex model. Let's start with introduction. In today's digital economy, data has become a valuable tradable commodity. And it possesses unique attributes such as replicability, dynamicity, and composability. The replicability means that the data's marginal cost for replication is nearly zero. And the dynamicity means that the data volume is not constant. It decays or evolves over time. And the composability means dataset can be integrated for higher volume, and a single dataset can be used after composed with others. And therefore, the data pricing must consider quality, and a unified systematic pricing paradigm is yet to emerge, and this motivates our research. Next is literature review. The first part of literature focuses on data quality and static pricing. For example, Battling proposed a fundamental set of data quality dimensions, including accuracy, completeness, consistency, and timeliness. And Heckman proposed a linear pricing model considering volume, age, and accuracy. The second part is about the stackable games in data pricing. A stackable games is pioneered by von Stackborg. It models hierarchical interactions with sexual decisions. In the game, the leader moves first and anticipating the follower's optimal response. In data pricing literature, for example, Yu and Zhang considered a monopolistic platform as a leader and the data consumer as followers. And B in 2024, they incorporate sellers competition into stackable data pricing. However, all the models are static, as they ignoring the time varying data quality and fail to describe continuous time dynamic evolution. There are also some literature, some research on dynamic data pricing consists of contextual dynamic pricing with unknown privacy evolution and fresh data pricing based on age of information. The limitation is really consider massive competitive sellers in the market, like hierarchical game analysis for multiplayer market structures. I want to stress it is the Mayfield game. The Mayfield game is proposed independently by Larry and Lance and Huang. And the Mayfield game problem is used to analyze systems with a large population of rational individual agents interacting with each other. The framework has been successfully applied across diverse domains, including economics and finance. And the integration of stackable games with Mayfield games has been explored in the literature. There are some theoretical works. For example, the Norwin first considered the linear quadratic Mayfield stackable games for large multi-agent systems and proposed the epsilon stackable Nash equilibrium. And Moon and Baza consider RQG Mayfield stackable games with heterogeneous agents, and they used fixed point solution method. And one in 2025, he considered Mayfield hierarchical control with sticky prices. And our main contributions is first to construct a three-tier dynamic market model. We consider a hierarchical architecture, including one buyer, one broker, and a large number of competing sellers, which is more in line with real data trading scenarios. And the second is we integrate game story methods. We combine stack game with Mayfield game and providing a rigorous analytical framework for large-scale dynamic markets. And the last one, we prove the existence of equilibrium. We derive the approximate optimal strategy for each entity and verify the existence of the epsilon1, epsilon2, and epsilon3 stackable equilibrium. Next, I will introduce our structure. We consider a three-tier stackable game. There are three classes of participants in the data markets. Data buyer, he acts as a leader. He actively proposes data product requirements and payments price PBU. As the initiator of the game, its decision objective is to maximize his own utility function, leading the market's price benchmark and the demand direction. And the second one is broker. He acts as a sub-leader in the game. The data broker acquires raw data from competitive sellers and pauses and resells it. And his decision variable is the price PBR and paid to the sellers. Its strategy aims to maximize the average profit. The third one is competitive sellers. their followers in the game model. They have homogeneous data resource and they can adjust data quality by incurring costs, with the decision variable being the quality adjustment strategy. The market structure is present in the following figure. The figure illustrates the hierarchical decision-making relationships and objectives functions between one buyer, one broker, and n sellers, constructing a closed-loop dynamic data trading system. Okay, next, let's introduce the model in detail. Firstly, we considered a complete probability space with a filtration satisfying the Euro conditions. Suppose n plus 1 independent Brownian motions, Wi, from I from 0 to n. For cell I, we use a stochastic differential equation to describe the dynamic evolution of data quality QTI. It's equation 1. This equation contains a mean reversion term, a quality adjustment term, and 2 types of noise, which fully reflect market complication and random disturbance. Firstly, is in the equation, the overlay Q is average of n data quality. It's a mean field term. And on the right-hand side of the equation 1, the mean reversion term reflects the pressure of the market. If a seller's quality deviates from the market average, it will be subject to an invariable pole to revert to the mean, ensuring the convergence and the stability of the overall market quality. And the sellers can change their data quality by investigating adjustment efforts tau I. Tau I is a quality adjustment strategy of the seller I. It's the control variable. And beta I measures the effect of adjustment input on data quality changes. And there are 2 Brownian motions. Wi is idiosyncratic noise. It represents the individual sellers, such as operational errors, technical failures, or some special events reflecting macro-level uncertainty. And the common noise W0, it represents micro-random factors affecting the entire market, such as industry policy changes, technological innovation, or macroeconomic fluctuations. And we define the control site in this page. Firstly, we denote F0 is filtration generated by the common noise, the Brownian motion W0, and LF0 to be the space of I progressively measurable real-valued processes X, and the norm is finite. And UBR and UBU be the set of F0 progressively measurable real-valued process, and their norm is bounded. There are a CT, a positive value CT, depending on T only. And there are 3 objective function. The first is the buyer's objective function. The average profit of the buyer is the difference between the quadratic utility gained from the data product and the payments to the broker. The broker's profit is calculated by subtracting the seller's payment and the manufacturing cost from the payment from buyer. The seller's profit is the payment from the broker minus the adjustment cost. And for the three-layer game problem, we give the following definition of equilibrium. Let bound tau star be a vector consisting tau star 1, tau 2, tau star n, and bound tau star minus I be the vector by replacing tau star I to tau I. And a vector of the Mistel strategy PBU star, PBR star, and both tau star is called an epsilon 1, epsilon 2, epsilon 3 stack block equilibrium if the following three conditions hold. The first one, as the bottom layer is an n-player non-cooperative game, we need the both tau star constitutes an epsilon 1 Nash equilibrium for given PBR. It is given the broker's price PBR, no seller can increase their profit by more than epsilon 1 through strategy changes. And for the broker and for the buyer, any changes of their strategy PBU and PBR won't increase their profit by more than epsilon 1 and epsilon 2 and epsilon 3. And following the classical solution method for the stackable games, which the solution idea is backward induction. We should solve the game problem from bottom to top. First solve the seller's problem, and then the broker's problem, and last the buyer's problem. Step 1, we given the broker's price PBR and analyze the non-cooperative game problem among all sellers, solve their Nash equilibrium strategies or tau star. And step 2, we given PBU and substituting the seller's equilibrium strategies into the broker's objective and solve the broker's optimal PBR star. And finally, we take up above results as known and solve the buyer's optimal PBU star. First, look at the step 1 is a seller's n-player game problem. The game problem is given by 5. Note that the mean field term Q over line is in the equation of dqti. So the key difficulty is when the number of sellers n tends to infinity, directly solving the n-player game involving interactions among all sellers became computational infeasible. as the dimensions of the states and strategy space explode. So we use the tool of mean field approximation. We obtain the mean field game problem for sellers. The mean field problems is we consider a fixed MT, M be a continuous process. We assume each seller is no longer in interaction with all others, but only with a mean field term MT, represents average behavior of the market as a whole, which is simplifying complex interactions. In equation 6, where W is a scalar Brownian motion with its independent of the former Brownian motions W0 to Wn. And the optimal control problem for the representative seller is the equation 7. And the control strategy tau star is called a mean field equilibrium if it's the best response to itself in the sense that MT equals the conditional expectation of QTM, and QTM star is optimal state under tau star. And we solve the problem 6 to 7 by using the stochastic maximum principle. And we obtained the following forward-backward stochastic differential equations 8. And the optimal strategy tau m star is given. Moreover, tau m star has the following state feedback form given by below, and this equation 9 and equation system 10. Next, we should deal with the fixed point problem. Let Q m star, Y m star, and Z m star be the satisfying the forward-backward stochastic differential equation. And we prove that there exists a unique continuous process m star satisfying the consistency condition, and also has the closed form given by the equation 11. There are the sketch of the proof. And now, next we construct the following strategy for N sellers. Based on the mean field equilibrium, we define the following adjustment strategy for sellers I equals 1 to N, given by the following equation. And then we can prove that the proposition, the vector of strategy we construct in the equation is an epsilon Nash equilibrium, and epsilon is equals to the order of N minus 1. This proposition is based on the following lemma. sketch proof of proposition 1 is listed here. Next, we focus on the optimal pricing problem for the broker. For fixed PBU and tau star, we obtained by the following equation. We investigate the optimal control problem confronted by the broker, which is formulated by the following equations. And the state system is given by 21. It's also a backward stochastic differential equations. So the key challenge is the cost of dimensionality and complex coupling structures. With n followers, the system involves three n state variables, making direct analytical infeasible for large n. So instead of tackling this original problem directly, we introduce the following auxiliary problem with a corresponding objective function and the state process. And by the variational analysis methods, we give the solution to the optimal control problem 22 and 23. The result is listed in the lemma. And now we apply the decoupling technique based on the four-step method to study the solvability of FBSDE. It then reduced to the solvability to the following Riccati equation, 26, and the matrix of the coefficients is given by 27. And we propose the following lemma. It gives the conditions to guarantee the Riccati equation.
Excuse me. You have just 2 minutes left.
Okay.
Mm-hmm.
And we prove that the asymptotic optimity of the proposed strategy for the broker. And next is the optimal control problem for the buyer. It has same key difficulty as in the broker because the state process is large. So we introduce the following representative agent problem is 31 and 32. And gives the following result to solve the problem. Lemma 4.3. And the solvability of coupled FBSD 33 is reduced to the solvability of RDE Riccati equation 33. We also provided the conditions to guarantee the existence of the solution to the Riccati equation. And we prove the same topic optimal strategy for the buyer. Here are the related literatures. And thank you for your attention.
Okay, thank you very much. We have just time for short question, please. As far as I understand, you can relate the speed of convergence of your optimal strategy with the speed of convergence to mean field equation of initial problem. Am I right?
Yes.
Okay. And because we have a lot of book devoted to Minfield games, for example, Kolokольцев book, and we have a backward stochastic differential equation for control problem with mean field equation. So it is interesting to compare your statement with the statement if we initially solve the optimal control problem for mean field and then say, okay, the solution is going with the speed like this. Okay, thank you very much again. And we have to switch to next talk. And the next speaker is Skripnik Nikita with the talk approximation of smooth knots. Please, Nikita.
Can you see my screen?
Yes.
Okay. Today I'm going to talk about approximation of smooth knots. Let's begin from a simple task. Let's build a function that makes from a simple octagon in two-space dimensional, the curve in three-dimensional space. Okay, we consider a regular unit octagon in a plane, and its eight vertices actually disturb on circle. Then we have to specify eight points in three-dimensional space. Now we are going to build a curve that passes through that eight points that's we defined on the previous slide. For that, we introduce parameterization of the curve. We use such parameters, and that's the final curve we built using that parameters. It looks like a linear connection of that points with rounded angles. With rounded angles here. Okay, and let's observe the tangent vector of that curve we got. Let's discuss a question. How many times does the tangent vector rotate around the origin? For that, we built three projections to look on tangent vector on each space of three-dimensional space. And we can see using that images that rotational image in of this curve is equal to 3. The curve built is the simple trefoil. Okay, now let's go to the theorem, the one result. We suppose that the curve is defined by a trigonometric polynomial of degree n, and then the tangent vector of this curve can perform at most n complete turns while moving along the entire curve. Okay, for that we want to write the tangent vector equation. Then we name the function q and then write the equation that's argument of tangent vector equal to, and let's write that delta argument of tangent vector equal to, and now we want to prove that this ending delta argument q is equal to 0. For that, let's define two more functions, g and h, and the condition to apply Schett theorem that was in theorem condition, so it's true. So we can apply the Schett theorem, and we get through this theorem that q and g have the same number of zeros inside the circle. So g is constant and not equal to 0, so there's no zeros. Therefore, delta argument of q is equal to 0. And as a result, we get that tangent vector of the function from the condition of the theorem is equal to n. Let's go to the next result. That's any continuous to periodic function in three-dimensional space can be uniformly approximated by trigonometric polynomial. We consider a smooth curve, as you can see on the screen. Any of functions x, y, and z are 2p periodic. So let's move on. Since each of these functions, due to the whole function, is smooth curve of class C1, so x, y, and z functions are also smooth curves of class C1. We can approximate them using trigonometric polynomials. So we get functions xn, yn, and zn that approximations of the original ones. So we can build the function that is approximation of the original curve that you can see on the screen. And it's close to the original one curve, and we can easily prove that, as is shown on the screen. Okay, let's move on the next result. Let's suppose that projection has only of the curve has only of the curve we project on the space, and let's suppose that that projection has only transversal double points. Then small perturbations of the curve that we get while approximating this curve do not change the number of crossing. Let's look on the double point, and from the transversality we get that the functions that are tangent vectors in that point are linearly independent. Then we can use implicit function theorem, and we obtain that there's only one smooth function u from S, such as that u from 0 equal to 0. That the next condition is true. This gives us exactly one double point in a small neighborhood of the original one. Since the perturbation is small, the corresponding map remains a small perturbation of first one. Therefore, applying the same reasoning as before, we conclude that there exists exactly one double points in sufficiently small neighborhood of original intersection. Okay, and let's move to the last result. That no loops can appear under approximation by trigonometric polynomials. Closeness of the second derivatives can be proved in the same way as it was proved a few slides before, by dividing a function on three-dimensional functions. And therefore, no sharp changes can appear there beyond the sharp changes of the original curve. And this was proved in the work of Yuri Minarek, as you can see on the screen. So let's move on to the conclusion. First, we proved that a curve defined by a trigonometric polynomial of degree n, the tangent vector can perform at most n complete revolutions. Second, we showed that every smooth periodic curve can be approximated orbitally well by trigonometric polynomials. And first, we established that the approximation preserves important geometric properties such as a number of crossings and new crossings cannot appear, like new loops. Thank you for your attention.
Okay, thank you very much. We have a lot of time for discussion. Maybe someone have questions or comments, please.
I have a question.
Please.
So the question, since there are no new double points or loops, next natural question would be, is there possible to obtain some measure of how large changes are needed for them to appear? So how distorted can get the curve before these new double points appear? Are there methods or results? Because possibly one can think about writing down the explicit expression for the projection and studying it.
Maybe I have to answer. Surely, it is interesting question, and we already began to think about this. Actually, for non-smooth functions, we have an answer. For example, if we have self-intersections for Brownian motion curve in the plane, and we approximate it by polygonal lines, then if we use uniform partition like 1 over n of the initial time interval, then the speed of convergence to renormalized self-intersection local time will be like in Q formula 1 over logarithm in some power. But now, of course, we expect more fast convergence, and the problem is related to the following: how the complexity of the knot is related to the different norms of its of derivatives of the function which parameterize the knot. So I think that 2 years ago I proposed in some talk the estimation from above by the of the Möbius energy and consequently of the average number of crows and so on. But
Yes.
at least for now, this work is in progress, and we don't know the precise answer on that question. Yeah.
Thank you very much for explaining.
Okay, some other questions or comments, please. Okay, if not, if no any questions, then we have 15 minutes to the next talk. So enjoy your time. let's start our next talk. Speaker is Vadim Tkachenko with the talk Extension of Birth and Death Semi-Markov Processes Beyond the Moment of Explosion. Please, Vadim.
Hello, can you hear me well?
Yes, now.
Very good. So I'm glad to give this talk, especially at 5 p.m. on Tuesday, which is the usual time of our Malavian Calculus seminar. And this is a talk based on our joint work with my scientific advisor, Andrei Yurievich Pilipenko, at the Institute of Mathematics. So I will try to find the balance between not getting you bored or not getting you overwhelmed, and hopefully provide some value. Let's start with the motivation and the context for our problem. So classically, we model particle motion or population dynamics as a Markov process. We can think of modeling some population, for example, and our state space is just natural numbers with zero, and the process represents the number of individuals in that population. The population stays at the constant level for some time, and then it may change. It is very convenient and pretty general to consider birth and death processes. The key property of such processes is, of course, the Markov property, or memorylessness. And this property forces exponential holding times. So the time which our population stays the same must be exponentially distributed. But it turns out that in recent years, many systems were shown to exhibit different behavior, so-called anomalous diffusion. In such systems, particles may have holding times with heavy tails, for example, alpha-stable distributions. And the answer to this was continuous time random walks or semi-Markov processes, where we can allow for arbitrary holding time distributions. Such processes are not Markov in general, but they must have some kind of regeneration property. We will talk about this in more detail. And I give a couple of citations here. Those two papers have some couple of thousand citations. So it seems like people found many applications in different fields of science. I'm going to focus on, so the first part is how can we model a process and where, in which cases this process is well defined for all moments of times. And the next question is, if the process has is explosive, when can we extend this process after the moment of explosion? So let's proceed with the statement of our problem and start with the definition. So we first consider a birth and death Markov chain from on natural numbers with zero. From any state n, our Markov chain can jump either right with probability pi or left with probability qi. And we have a strict reflection at 0. This is a very useful technical assumption. We can think of it as modeling a population, and if our population dies out, we add one individual to that population. Now we construct a continuous time process that follows this transition of the Markov chain, but stays some random time at each state before making a jump. But we want this process to have some kind of renewal or regeneration property. So here's what we do. For each waiting time tau I, we consider a sequence of its independent copies. And we assume that all these sequences and the Markov chain xk are mutually independent. And using these random variables tau, we construct a sequence of jumps recursively. So, for example, we start at 0. We take a 0th copy of the variable tau 0, wait that amount of time. Then our Markov chain jumps to the right. We take a independent copy tau 1 0, because it's the 0th arrival at 1, and wait this time, and then continue transitions. So this is a formal way to define it. So our Markov chain tells us which variable we choose to wait. And now we can construct a process. So we just take the value of the Markov chain between the moments of consecutive jumps. We call this a continuous time random walk, CTRV for CTRW for short. And we say that it has an embedded Markov chain xk and waiting times tau I. The trajectories of such process will be Cadillac trajectories. So, for example, we start at state 1, wait some time, then we jump, for example, up, and so on. Each time we take a new copy of the respective waiting time. So, for example, when we, if we started at 1 and we got to 1 second time, we will take the next corresponding copy of waiting time. Okay, now let's talk about the phenomenon of explosion. Denote by sigma n the first hitting time of some state n. For example, if our process starts at 0, we can wait this amount of time, jump to 1, wait this amount of time, and we hit 2. So sigma 2 in this case will be just the sum of our waiting times. So tau 0 plus tau 1. And if we take the limit of sigma n when n goes to infinity, this will represent the time to reach infinity in some sense. And we give it the following definition. We say that the process X explodes if this sigma infinity is finite. This just means that our process completes an infinite number of jumps in a finite time. And this means that our boundary at infinity is attainable. And the first stage of our research was to establish analytical criteria for explosion. This is very important because if we try to model some physical process, which doesn't have this explosive behavior, we want to rule out when explosion happens and when it doesn't. Because if the moment of explosion is finite, it means that after this moment of time, the trajectories of our process are not defined anymore. So it's only defined on the finite interval. So introduce the following notation. Delta K is defined in terms of the transition probabilities of the Markov chain Xk. I recall you that Pi is just the probability of moving to the right from ith state, and Qi is the probability of moving to the left. And the next value is related with the so-called speed measure. Here, we also have transition probabilities P and Q, but we also have this value, which is a 1 minus the Laplace transform of the waiting times, traditionally, for Markov processes, we would have the average waiting time, the expectation of tau I. And this value says something about how quick our process moves through the state I. In our more general case, the expectation may be infinite, and it is not allowed to use it in general. But this value plays the role of the speed measure in our case. Okay, and here we have the explosion criterion. It was so it's the previous work. What we have here, we have a criterion that says that our process explodes with probability 1 if and only if the following two series is convergent. And this series closely resembles the conditions for diffusions. Here we actually have a discrete integral of the speed measure over the scale. And for example, for Brownian motion and other diffusions, we have the criteria of attainability of a boundary in the terms of the scale and speed measure for the process. So now we have a purely analytical criterion, and we know, just looking at the parameters of our process, if it is explosive or not. And the next question that we ask is, well, okay, our process is explosive. It means that it is defined only up to some finite moment of time. Can we extend this process for all moments of time? So after the moment of explosion. And I can go to the next slide. Yes. So this is exactly what I said. We consider an explosive case. Our trajectories are defined only on the finite interval. And we want to construct an extension. And what do we mean by that? We want this extension to behave as our initial process X before it hits, before up to the moment of explosion. And then when it moves through the state space n0. And we want it to have a sort of instantaneous reflection at infinity. So when the explosion happens, the process immediately returns to the initial state space.
So,
and
if I understand right, the problem is to find the distribution after such explosion, yeah, from where you will start again. Am I right?
Yes, this is also one of the questions. But initially, we don't even know if there exists such an extension, in some sense.
Okay.
Okay. And to define everything properly, we have the following topological setup. We take a one-point compactification of our state space. We add the point at infinity, and we consider the following metric. Or alternatively, we can move to another state space where we take each natural number and move it to something like this. So our infinitely far point will be moved to exactly 1, and we will have a compact state space. And we will consider the Skorokhod space of Kadlak functions with the J1 topology. We take the proper 1 such that our space becomes complete. Okay, and here's how we construct, here's how we prove the existence of an extension. We consider a sequence of processes xn with the same characteristics as the initial x, but we change its transition probabilities. So at a fixed level n, our processes will have a strict reflection. So they can get to the state n, but they are forced to jump back to the n-1. This means that our Pn becomes 0 and Qn is 1. And we have the following important idea to prove the existence. The idea is pretty straightforward. We want to approximate our process that reflects from infinity with processes that reflect from a finite sort of wall. And we want to move this wall to infinity and show that there exists some limit. And the construction is the following. We build all of xn on the same probability space using synchronized state visitation counters. So basically, each elementary event defines a whole matrix of waiting times and transitions. So, for example, we have this matrix here, and this is one realization. At state 0, we wait this much time, and after we jump to 1 up. Next time, when we visit 0, we use this much time and jump to 1, yes, and so on. And we use the exact same realizations of such random variables for all of our processes xn, even with different n's. And it is, I think, more convenient to show this on a picture. So here we have a simulation that I did. It's not perfect, but it will do its job. Here we have 3 processes, x5, x10, and x20. So x5 is reflected at level 5, x10 is reflected here, and x20 is reflected here. We already moved to a compactified state space for this picture. And what we see here is the following. These processes start at 0, and they wait exactly the same time at 0, and then they jump, so we can call it tau 0, 0. Then they jump 1 up and wait this much time, jump down, and so on. They are synchronized. Then, when our smallest process, x5, hits its boundary at 5, it gets reflected to 4. And then we have another displacement where our process x10 hits its reflective boundary. So these processes stay synchronized before they arrive at the reflection boundary. And what's also important here, let's take a look at our blue trajectory and our orange trajectory. When our blue trajectory got reflected to the state 4 and then jumped to 3, the trajectory looked like this. And it's not perfect because of the resolution. Yeah, so probably it made 2 jumps here. What we see when we look at our orange trajectory is that when it finally returned to the state 4 and 3, its trajectory started looking the same as the trajectory of x5. So this is what we mean by synchronization, and this property will play an important role. So for the limit to exist, the time spent out of sync, yes, must vanish. And let's introduce the following variable. We will call it theta mn, and it's the time that the process xn spends in the interval mn before it returns to 0. So basically we have a reflective boundary at n, and we have some state m which is smaller. We consider our trajectory. I'm going to draw it in a simplified manner. And we count how much time our process spends in this interval, in this tube. And the idea is to show that this time is small. Let's recall that nu I is our speed measure. It's defined as follows. And we had the following result, which says that our time spent in the region between m and n is sort of uniformly small in probability. And this is equivalent to the condition that the speed measure over all states is finite. But this convergence in probability is not very useful. And recently it turned out that we can easily get an almost sure convergence. And to do that, we need to utilize our coupling that I described earlier. The coupling gives us the following nice properties. For every single realization omega, this time theta will be strictly monotonic, because we just add additional time to the sum of waiting times. So we can easily see it here. For example, if we compare the blue and the orange trajectory, this orange trajectory, it spent more time and then it returned to the same state as the process x5. And next we do some technical estimates, and we are able to link the Laplace transform of this time theta with the speed measure and establish the following analytical bound. And if we assume that our speed measure is finite, this would mean that this will converge to 0, and this forces the time theta mn to converge to 0 almost sure. And this would mean that our total difference in time will vanish almost sure. And now we can formulate the first main result, the existence of the extension. So the total time of these unshared excursions goes to 0 almost surely. And because of the way we constructed the state space, because of the choice of our metrics, the space difference is uniformly bounded. because all of the trajectories, we can think that they live in between 0 and 1. Yes, so after some moment of time, the spatial difference becomes uniformly small, and the time difference was also shown to be uniformly small. And this allows us to go to pass to the limit in the Skorokhod J1 topology. So let's state the following theorem. Let our X be a continuous time random walk or semi-Markov process, as was defined earlier. And suppose that the respective scale function and speed measure are finite. So the series with delta and the series with nu is convergent. Then the sequence of our reflected processes, reflected from n, converges almost surely in the J1 topology of the Skorokhod space that we introduced before. And this condition is exactly the condition of a regular boundary of a diffusion. The scale is finite and the speed measure is finite. So we have many connections with diffusions, and it's actually not surprising because...
Excuse me, can it happen that when you will have the limit, this limit will spend non-zero time in the infinity point?
That's a great question. I'm going to talk about this just in a moment. Yes, it's a very, very important question. Yes, I wanted to say that our birth and death processes are like the closest approximation of continuous processes when we talk about processes on a countable state space, because they can jump only one state at a time. Their trajectories are so they have very similar behavior to continuous processes, diffusions, and this means that we can probably use some results for these processes to obtain some results for diffusions or for processes with continuous trajectories. And the next property of our limit is some kind of regeneration property. When we choose some moment, some number k and some state m, when we when we hit the state m at any kth time, this will be a moment of regeneration or so-called renewal time. This means that our process is independent of its past trajectory and behaves as a process that was just started at state m. And we again prove it via coupling. And the main thing here is that when our process, our limiting process x tilde, comes to the state m, it uses the same unused random variables for the future trajectory. And by construction, these random variables are independent from all the previous. And this, let me state the theorem. Yes, so the limit process inherits the renewal property at moments t of this type. Yes, so we don't say that it has a Markov property or it has yeah, so we choose a specific moments of time that are easy to work with. And now the question from Andrei Anatolievich. So is this continuation extension unique? Can we extend it in some other natural way? And it turns out that we, of course, can extend the process after the moment of explosion in many different ways. For example, we can just say it to hold there. Yes, I have 1 minute. I think I will be in time. So the next main result is the characterization. So suppose we have some Cadillac process on n0 with infinity. It has the same distribution as x up to the moment of explosion. It has this regeneration property, and it spends 0 time at infinity. And then this process is, so it coincides with our constructed limit, has the same distribution. And it means that we have a way to extend our process uniquely with the following characterization. And here is a short summary. So we can extend the process if the scale and speed measure is finite. We use it, we prove it using the maximal coupling. And we will have a process that explodes, goes to infinity, and then can undergo infinitely many bounces of infinity in a finite interval of time. So this is all from me. Thank you very much for your attention.
Thank you for interesting talk. Please, we have a time just for one short question.
I have a short question, a comment, which is development of the question I asked on the previous conference, that theoretically you can try to reverse the scale to obtain results about the behavior of the diffusion when it approaches 0, whereas the 0 is the exit or regular point, but the diffusion goes to 0, so that's a problematic part. And maybe it is possible to obtain some results of classification whether it's a regular point and an exit in terms of this series, which can be obtained from the continuous process, read from the continuous process.
This is a very interesting idea. Yes, thank you very much. I think we have something similar in mind with Andrei Yuryevich.
Yeah, it's natural, I think. Thank you.
I think that in book of Shiryaev and Cherny, they have some classification of zeros for diffusions exactly in terms of scaling and speed measure. So
yes, but
I think that something is done in that direction.
Yes, I know about that result, but I think that here can be an analog of that in this discretized setting can be obtained.
Why not?
Or maybe we can show something for sub-diffusive processes. Yes, but thank you. It's interesting.
Okay. We have to switch to the next talk. And our next speaker is Yuri Minyalik with the talk Topological Types of Moving Random Link. Please, Yuri.
Okay, thank you for the opportunity to give a talk. It is always a big pleasure for me to participate in Skorokhod readings, because Skorokhod was not only a great mathematician, but he was also a great person. Okay, so the subject of my today's talk is topological types of a moving random link. So let's start with some short introduction. So knots and links arise in fluid mechanics and vortex dynamics. And as we know from theory of differential equations, such motions can be pretty chaotic, so they strongly depend on initial conditions. So one can look at dependence of trajectories with respect to initial conditions and make small perturbations. And then we can look at these trajectories as random. So this is the interest of studying these random links from this viewpoint. Also, there is another viewpoint which arises from biology, where there is a well-known fact that long polymer molecules, their chemical properties depend not only on its chemical composition, but also on its spatial geometry. So we can have polymers that have the same composition but different geometry and so have different properties. This is kind of what gives the interest in studying this random links. And let's start with motivation of the construction that we propose. So what we want, firstly, is what we think of moving random link. We say that it is such that for any moment of time with probability 1, it is a pair of closed curves which don't intersect and don't have self-intersections. And we also want it to satisfy 4 conditions. We want it to be smooth, to be regular, so the derivative is non-zero everywhere. We want it to achieve any topological type with positive probability, so we can expect any possible link to occur. And also we wanted to change its topological type during the motion. It is actually very natural if we look at biology, where we can have the situation when, for example, in our body, we have this polymer molecules and there is maybe other molecules that can just join and make a cutoff and then rebuild the polymer. So the composition remains the same, but geometry change. So we want it to be like the same. And from this point, we arise to following construction. So our idea is consider an image of two non-intersecting circles in plane by Ornstein-Uhlenbeck stochastic flow, which we'll denote by XIT. And we will understand why it creates random links. And we will consider 2 models. So in first one, we will move simultaneously both components of a link. And in the second one, we will move only the second component and the first one will be remain fixed. And we will look at topological and geometrical properties of obtained moving random link. So let's consider a precise construction. So suppose that W capital is a Wiener sheet, H is from L2 R squared with the following conditions, and then consider the following SDE, which we can explicitly integrate, and we get XIT. So XIT right now, it is a Gaussian random field with independent coordinates. It is centered, it is isotropic, and we have a form of covariance, which is exponent of -1/2 the distance between U and V squared. We will denote it as J capital for future formulas. And we can see that our covariance is of very good form, and then one can actually prove that our random field XIT has infinitely differentiable modification. So that means that if we consider image of circles, it will be a smooth closed curves. This is what can we already say. And also I want to give a remark that distribution of XIT doesn't change with time. Okay, so next is a key theorem about construction of random knot. It was proved by Andrei Anatolyevich Drogovtsev, and originally it was all his ideas of this construction of random knots. So he considered an image of unit circle under this Gaussian random field, and he proved that with probability 1 it is a smooth knot, and that it attains any topological type with positive probability. Our goal is to prove the similar statement for random link. So what we do is we consider 2 non-intersecting circles on plane, consider their images, consider this union of curves, and what we want is that with probability 1 it is smooth, it is regular, and that it attains any topological type with positive probability. That is our goal to understand the proof of this result. So the first of these 3 propositions was proved by me in my paper of 2025 that this gamma is indeed a smooth random link. The idea of the proof was very similar to the corresponding proof in the work of Andrei Anatolyevich. So let me quickly recall the main idea of the proof. So the first step is that these two components are smooth random nodes due to the stated theorem. Also, we define functions h epsilon, which approximate delta function at 0. So right now, B is a ball with center 0 and radius epsilon. And one can get the following lemma that such limit as epsilon tends to 0 exists. It is finite and equals to this integral. Let me recall that J from U right now is the E minus 1/2 norm from U squared. So because our theta 1 and theta 2 are these circles, they're not intersecting, so there is denominator is non-zero, so integral converge, everything's fine. And the last step is that we prove from contradiction if gamma 1, gamma 2 have intersection with positive probability, then we consider this ball of radius epsilon at the center of this point of intersection. And as we stated before, our Gaussian random field is smooth, so gamma 1, gamma 2 are smooth, so they're continuously differentiable, so they're Lipschitz, and so the growth of them is at most linear, yes? And then each of those arcs spent in this epsilon ball time, which will be proportional to epsilon. So when we consider pairs of time moments, for which they're balls in this epsilon ball, the measure of them will be like epsilon squared. So we can write like that it will be something like constant epsilon squared, and h epsilon have epsilon cube in denominator, yeah? So it will go to infinity as epsilon tends to 0. So this is like the idea of why existence of this limit contradicts having intersection with positive probability. Okay, this is how one can prove that this is a smooth random link. And also in the same manner, one can prove that it is regular. The proof is in very similar manner. It is even a little bit simpler. So I think we will not spend time on this and move forward to the question of why our random link attain any topological type with positive probability. But before this, let me quickly recall two characteristics of a link that we will discuss during the talk. One of them is linking number that one can define using Gauss linking integral. So this such integral where we have determinant in numerator and this norm of difference cubed in denominator. It is a hard definition, like to start with. So it is simpler to say that linking number is the number of times that one component of a link wraps around another. So it is always an integer. We consider also no rotation, so this number could be negative. And I recommend this paper slash survey of Renzo Enrico and Bernardo Nipoti, where they really wrote down like 4 different definitions of linking number and different proofs of equivalence of those definitions. So I really recommend it if you're interested in this topic. Okay, another characteristics arise from number of crossings. So we just count the number of crossings when we orthogonally project our link on plane in direction p, where p is unit vector. We count these intersections, which are exactly between two components. So we don't count these self-intersections. And then using this number of crossings, one can define this average crossing number. It is an average value of this number of crossings among the unit sphere. So it was defined by Friedman and Zheng Hu in their paper of 1991, where they proved that this characteristic is well defined. And what is the most interesting? They proved the following formula for average crossing number, that it is the same as linking number, but the difference is just the absolute value inside the integral. So this is very interesting because linking number is always an integer, and this average crossing number, it can be any number from 0 to plus infinity. And they have different origins. but the difference is just absolute value inside the integral. So it is useful for us because we can prove various statements simultaneously for both of them. For example, one of those statements is the existence of moments in our situation. It was again proved by me in my paper that we have moments of order up to 3 half not included. Proof is very technical, just some bounds and Gödel inequality. So nothing really interesting. So now let's come back to the question of topological types. So firstly, let's consider definitions of what we think is that two links have the same topological type. We will say that smooth links are equivalent or have the same topological type if exists orientation preserving diffeomorphism which maps one link to another. This is the first definition. The other definition is equivalent to the first. It says that if we have a smooth ambient isotopy that maps one link to another. So this is like a flow of diffeomorphism. So the second condition is requires more, but it is at the same time more useful to prove various statements. So one can imagine this like this picture. So we have these two knots which are equivalent. They're both like trivial knots, and these like gray lines can be interpreted. They can be viewed as lines of motion during ambient isotopy. Uh, Actually, they might not be like moving like this. They can be like staying at the same place, but just like uh, so it is. But if so, to be clear, I draw such an image. So this how it can change during ambient isotopy, and this orientation preserving diffeomorphism is just we jump from beginning to an end straightly. Now let's formulate this statement. That our random link attain any topological type with positive probability. So to prove this statement, the proof is pretty long and have a lot of technical details. So let's just discuss two main points of this proof. The first one is from theory of Gaussian measures on infinitely dimensional spaces. So if nu is Gaussian measure on separable Banach space such that support coincides with whole space, then the measure of any open ball in this space is positive. It is like the first point. And second point is that if we consider X is such space which consists of pairs of continuously differentiable and 0 to pi functions and such that they have equal values at endpoints, and we have this norm, then X is a separable Banach space. And one can consider nu as a distribution measure of gamma t11 and gamma t21. So it is a first coordinate of first component of random link and first coordinate of second component of random link. Then one can prove that support of this measure coincides with X and nu measure of any open ball next is positive. Like this is two main points of the proof, but I think there's a lot of people who think right now, why do we consider this space X with this norm, and how does this norm is really connected to topological types and everything? And there is actually a very interesting connection between them. So it arises from a following question. In which sense we need to have closeness between two links so that they become equivalent? And one of the possible answers was given by Dan and Sullivan. They gave the following definition. They said that two rectifiable links are delta theta close if there exists a homeomorphism between them such that corresponding points are between distance delta of each other and corresponding tangent vectors are within angle theta of each other almost everywhere. So they control the distance between links and the angle between corresponding tangent vectors. And they say that for any fixed link gamma, continuously differentiable, we can find such small delta zero such that for any link gamma prime, which is delta theta close to gamma and delta is less than delta zero and theta is less than pi divided by 6, it is actually interesting that this angle needs to be just less than 30 degree and not just super small. Then gamma and gamma prime are equivalent. So in our consideration, it will be more useful for us not to work with these angles between tangent vectors, but work with derivatives. And it occurs that in our situation, and let me recall, in our situation, links are regular, we can prove a more useful statement. So let me present this lemma, which is one of the most important results in this talk, which says that for regular links, if we control a distance between links and we control the distance between derivatives and make them small enough, then the links become equivalent. And this lemma builds this bridge between topological types and these measures of open balls and Banach space that I defined previously. So this is a really interesting statement. And this statement gives us opportunity to consider another object. It gives the opportunity to define precisely space of links. So what we do, we write B is the pair of closed continuously differentiable curves in space, and we take the norm as such one. So we have this maximum of norm plus maximum of norm of derivative. This space B is separable Banach space. And in this space, we can consider a set of all regular smooth links X. And our random link lives in this space X. And we can use our lemma to prove a statement about the structure of this space of links. It occurs that the equivalence relation between links split X incountable amount of open connected in X regions. So we have U1, U2, and so on. They are all equivalence classes in X, and they will be open and connected sets. This is what interesting. And I want to present a full proof of this result because it is pretty simple and it is like have this topology like flavor which uses the proof uses the idea of open and closed sets simultaneously. So let's take an arbitrary link from X and suppose that U is a connected component of X which contains gamma. So U will be open because right now balls are connected sets, so connected component must contain this ball. Now we want to prove that U is an equivalence class. To do so, we take arbitrary gamma prime, which is equivalent to gamma, and we want to show that gamma prime is an U. So we use the definition of equivalence of links using smooth ambient isotopy, Fxs, and we consider gamma s is an image of gamma at the time s, and we define all indices such that gamma s is equivalent to gamma. So from our lemma, which states that if in X our links are close enough in norm, then they are equivalent. So from this and from smoothness of ambient isotopy, one can get that Y will be open and closed at the same time. So then, because 0, 1 is connected, Y will coincide with hole 0, 1. So then gamma prime will lie in U, and U will be indeed equivalence class. And the last step is to notice that B is separable, as then X is also separable. So there are at most countable amount of disjoint open sets in X. And this statement about structure of space of links can help us to quickly get some interesting results. For example, linking number is continuous in this space X with respect to defined previously norm, because right now linking number is locally constant. So on each U1, U2, and so on, linking number is constant because they represent equivalence classes. And right now, linking number is a topological invariant. So if we have equivalent links, then linking number is the same. Now let's go back to models of moving random link. So the first model is that we move simultaneously both components. So gamma t consists from gamma 1t, gamma 2t, and we're moving them both. So let me recall that gamma t right now doesn't change its distribution during the motion. They are all identically distributed. And we have this very interesting statement, which says that during this motion, gamma t will attain any topological type infinitely many times. So any link with two components that you can imagine will occur infinitely many times during this motion. And this result comes from two lemmas. The first one is a generalization of Borel-Cantelli lemma. It is the lemma which was proved by Erdos and Rini, where they got rid of condition of independence of random events, but instead they wrote this second condition, which is some sort of like weakened condition of pairwise independence. So for example, if we have like a limiting pairwise independence of these events, then this condition is satisfied. So in our situation, if it is unclear, an is event gamma t n is equivalent to gamma capital. And due to the theorem about topological types, probability of an are all just the same number, which is positive. So first condition is satisfied, and we need to show that the second condition is also satisfied. And to do so, we need some sort of like this limiting pairwise independence between these events. And we can prove it using by proving strong mixing property in our case. So there is a statement of Rosenblatt that if the spectral density of a stationary Gaussian random field is positive and continuous, then it is strongly mixing. And we can apply this proposition in our case and obtain this conversions for our events, and then finish the proof using Erdos-Rini lemma. This is what interesting about the first model of moving random link. And the second model of moving random link is that when the first component stay fixed and the second one is moving. And in this case, the distribution change during the motion. And what actually happened is that in our space B, in which space of links live, we have weak convergence. Weak convergence to a link which have independent components. So this is what happened in this model. Two components of a link become independent from each other when t tends to infinity. And also one can prove in this situation the convergence of first moments. We know that they exist. And one can prove such good conversions. So this is what about the second model. And this is basically it. So there are some references, but I think I already wrote everything before. So thank you for your attention.
Okay, thank you very much. And maybe someone have questions or comments, please. Let me do a small comment that when Yuri introduced this space X, now it is clear that our process, if we consider the random process with values in this space of links, looks like a diffusion which switch between different domains where we have different topological types. And of course, the next our aim, one of the next of our aims will be some kind of excursions measure for this process in the space of links. So I hope we will continue the work in this direction and see what happens. Okay, if there are no any questions or comments, then we will switch to next talk. And next speaker is Alexander Lubimov with the talk Polynomial Regression Model and a mixture of the classical and Bergson errors. Please.
Yes, thank you. So, good evening. Let me share my screen. So, can you hear? Can you see the presentation?
Yes.
Yes. Okay, thank you. So, first of all, I'm glad that I'm able to talk at such a great conference like Skorokhod Readings, and I'm grateful for the opportunity to do so. I will tell about the polynomial regression model and the mixture of classical and Bergson errors, and this work is joined with Alexander Kukush, and I'm thankful for the invaluable guidance throughout the process of work on this subject. We deal with the following polynomial regression model. It has two errors. So first of all, y w, it is the observed argument variable, random variable, and delta is the classical measurement error, which arises when we try to measure x. Then xi, it is the sum of x and u. U is the Bergson error, and y is the observable response random variable, which we decompose in, which we introduce in the following polynomial form with respect to xi. So epsilon, it is the unobservable, epsilon, it is the error in response, u, it is the Bergson error, and delta is the classical measurement error, and we have the unknown parameters like regression parameters and the variance of the error in response and the moments of the variable x, random variable x. Yes, so based on the identical independent copies of this model, our aim is to estimate strongly consistently the known parameters and to study their asymptotic properties. First of all, I'd like to say that the linear model for the case where d was equals 1 was in detail studied by Kukush and Yakovlev. And actually, this work is the continuation of that research. It is important to mention that these regression models, and in particular the errors in variables measurement models with a mixture of classical and Bergson errors, arise in the radium epidemiology. It is so this mixture often arises when we consider the when we try to assess the risks of some large-scale radiation accident, like Chernobyl accident of 1986, and these errors, they arise in the following way. So, for example, if we have some city in which the nuclear accident has happened, we want to predict the distribution of the radiation throughout the city. It is the random variable. So actually, the radiation this random, and the distribution of it is a random variable. And our aim is to predict the risks of radiation accident on the citizens who live in the area around the source of this radiation. And when we and yeah, when we and the errors, they come from two ways. So the first way is that when we try to predict the distribution of radiation, we cannot do it we cannot do it accurately, and we have some error during the prediction of the distribution of the radiation. And on the other hand, when we measure the dose of radiation which has affected a certain person under the measurement, we also have the measurement errors. So we obtain the complicated model with the mixture of different errors. And it is important for these purposes to deal, to try to cope with this mixture of errors and obtain the estimators, good estimators for the unknown regression coefficients and the variance of the error in response. We introduce the following assumptions. First of all, the errors, they should have they should be the random variables of mean zero, and in addition, we suppose that the random variable x has the finite 2Ds moment. In addition, we suppose that x delta u and epsilon are mutually independent, and for the estimation, we need the following assumptions. We need the fact that we know the values of the moments of delta from 2 through 2D, and the moments of u from 2 through 2D. And in addition, in order to obtain the statistically determinable model, we impose the fifth condition, which states that the distribution of x is not concentrated at d or fewer points. So this fifth assumption is important for the I should say that all the three last assumptions, they're important for the statistical identifiability of the unknown parameters. So for instance, in the work of Kukush and Yakovlev of 2021, it was shown that we have to know the variance of the Bergson error in order to estimate all the unknown parameters. Otherwise, the model would be undefinable, unidentifiable, and the simple example was shown in that work. Since we have for the polynomial regression of the order D, we should also generalize this assumption from their work to the following. And the fifth assumption, it is also present in the work of Kukush and Yakovlev implicitly, because in the assumptions in that work, you may see that the variance of x should have been positive, which was synonymous to x being that the support of x having at least 2 points. So, the fifth condition is actually the generalization of that assumption. So, in order to obtain the identifiable model, we should suppose that distribution of x, that the support of x has at least d+1 points. So, in order to construct the estimators for the known parameters, we use the correct score approach, which is quite standard for the purpose of dealing with regression models with different errors. So our if we consider our model and if we suppose that all the errors in it are absent, i.e. i.e. the observable W is equal to X and it is equal to Xi, then the estimator for the unknown parameters would be given by the least square estimating function, which for the regression coefficients beta looks like this. And and according to the corrected score approach, our aim, our goal is to construct the corrected estimating function which satisfies the following condition of expectation equality. So our estimating function looks as following. So it is the some matrix d plus 1 cross d plus 1 matrix which depends on observable W times regression coefficients beta minus the vector column of length d plus 1 which depends on observable W and observable Y. And in order to construct the function which satisfies the expected conditional expectation equality for the corrected score approach, we want to construct the matrix H in a way that the conditional expectation is equal to the matrix given by this expression, and so actually given by rho times rho transposed, and construct a vector H so that in its conditional expectation is equal to the vector rho times Y. And the procedure of construction, it consists of 6 steps. At the step 1, we construct the polynomials TR such that the conditional expectation with respect to the distribution of x is equal to x in the power of r, and it is easily done via the Newton's binomial formula and the fact that classical measurement error delta is independent of x by our assumptions, and it allows us to compute all the polynomials recursively. Next, at the step 2, we define the matrix T of W, which is simply is following. And observe that this matrix satisfies the following property, the following equality, the conditional expectation of TW with respect to X is X times I plus J for the cell IJ. And yeah, and note that all the metrics we deal with, they have indexation which starts from 0 row and 0 column. It is more convenient for our purposes. Then we so we find coefficients beta x, which depends on in terms of beta and in terms of u, so that y can be y can be written in the following polynomial way. So and it is again a simple application of Newton's binomial formula and expansion of all the xi's in the formula of y in our regression model. So next we construct the vector h so that it is equal so that it satisfies the following equality. So again, since delta is independent of psi, it is independent of x, it is independent completely of y, it is independent of x, and thus it is independent of y times x to the power I, and therefore we may write by Newton's binomial formula by expanding W as x plus delta, we may write that it satisfies the following, all the y times W to the power of I satisfy the following equality, and we may obtain the yxj, we may obtain yxj via this system of linear equations. By simply introducing the matrix Z, we may write that our vector H has to be as follows. Yeah, for example, it has to be as follows. Next, we compute, we evaluate the expected value of the introduced parameters beta x, but they were not parameters; they were actually random variables, and we may evaluate them as follows. So notice that by the definition of the random variables beta x u, we have the following equality, which is really easy to see. And then since we constructed the matrix TW so that its expected value was equal to the expected value of x times x transpose, and we constructed vector H so that its expected value was equal to y by x and so on by x in the power of t. We conclude that beta can be evaluated in the following way. Okay, yes, and then at the step 6, we may evaluate the parameters beta, and it is simply done via the formula which connects the parameters beta x and parameters beta, and then we obtain the final formula which allows us to construct the strongly consistent estimator. So the strongly consistent estimator is following. So we we take the matrix T we constructed, we take the vector H we constructed, we take the arithmetic averages of these constructed objects, and we invert this matrix T bar, and multiply everything by the matrix U transpose to the power -1. Yes, and the corresponding estimating function is the following, and note that due to the constructions we have that if we take the expected value of this function by the distribution of y and x, we obtain the classical least squares estimating function, which was stated at the beginning. Then we proceed to the estimation of the variance of the error in response. So again, recall the model, and if the errors were not present, then we would simply estimate the parameter of variance by the following least squares estimating function. But if the errors are present in our model, then we have to construct our estimating function in a way that its expected value is equal to the expected value of this estimating function, and it can be done by finding the vector v, which in our construction depends on w and the parameter beta, so that its expected value is exactly the expected value of y times xj, and obtain the corrected estimating function. So it is simply done in 3 steps. So first we construct the polynomials which depend on w, so that the expected value is equal to the moments of xi, and it can be easily done by our previous construction of the polynomials tr and the again Newton's binomial formula. So the expression for the polynomials gr is following at the bottom. Next, we construct the matrix. So the construction is similar to the construction of the matrix T, and it is defined as in the following way. And evaluate in order to evaluate the variance, we may simply know that the error in responses are orthogonal to this polynomial component of the formula for y, and we may simply compute its this variance via the formula, and then we since we constructed the vector v yes, so since we constructed the matrix G, so that its expected value is equal to the expected value C to the power I plus J, we conclude that this vector is as following. Yes, and then we may substitute it in the expression for variance of epsilon and obtain the following evaluation, yes, which allowed us easily to construct the strongly consistent estimators for this parameter. So the strongly consistent estimator for this variance is as following, and the corresponding estimating function is as follows. Yeah. So we highlight that in the linear case, our estimators, they coincide with those which were present in the work of Kukush and Yakovlev, in which they studied the linear model. And I would like to note that the assumptions we imposed in order to have that strong consistency of these estimators, they also they also coincide for the case d equals 1. So for the case d equals to 1, our work completely coincides with the work done by Kukush and Yakovlev. So also I would like to give the example of the estimators for the case when we have quadratic regression. So consider the following model. It is the quadratic regression, and the estimator for beta can be found in the following way. I have quite large expressions here, but they are as follows. Yes. Yes, note that in our case, the estimation of the regression coefficients beta also relies on the variance of the Bergson error. And it is interesting to mention that in the paper of Kukush and Yakovlev for the linear case, it was shown that their estimators for beta, they do not use the variance of the Bergson error. But in the quadratic regression, we use this information also. And the estimator for the variance is as follows. So this also, these expressions are also quite large. Yes, and also it is interesting to study the asymptotic normality of constructed estimators. It is important for the construction of the confidence intervals for our parameters. So, but in order to manage to do it, we have to observe that our estimating function has following nice properties. And I should say that during the construction, it was the aim so that this estimating function has these nice properties. Yes, first of all, this estimating function is unbiased, which means that for the true values of parameters beta and variance of epsilon, we have the expected value of this estimating function being equal to 0. And in addition, it satisfies the estimating equation. So the arithmetic mean of the values of this function is equal to 0 if we substitute instead of beta and variance of epsilon their corresponding estimators, which we have constructed. Yes, and this theorem on asymptotic normality is following. So consider the following condition 6, which is important for the correctness of the covariance asymptotic covariance matrix sigma, which is written in the statement of the theorem. So if all the previous conditions we imposed, and in addition the condition 6 are satisfied, then our strongly consistent estimators, they are asymptotically normal with the multiplier square root of n. And this vector converges in distribution to the centered normal multivariate distribution with the asymptotic covariance matrix. And in addition, if the support of classical measure contains at least d+1 points and the support of the error in response contains at least 3 points, we have that these, yes, and the eldest regression coefficient is non-zero, then we have that the asymptotic covariance matrix is non-singular. And we may compute this matrix. So since our estimating function has nice properties, we may evaluate this asymptotic covariance matrix by the following sandwich formula, where v is the expected value of the derivative of our estimating function with respect to parameters, and c is the covariance matrix of the random vector S. Yes, and these expressions, they allow us to construct the strongly consistent estimator for this matrix. So assume that the conditions 1 through 6 hold, and the matrix defined in the previous theorem can be estimated in the following way. So it is easily seen via these expressions, and note that the condition 6 is important for the strong consistency of these estimators present here. Yes, so in conclusion, I'd like to say that we dealt with the polynomial errors in variable regression model under a mixture of the classical and Bergson errors. We managed to construct strongly consistent estimators for the unknown regression coefficients. In addition, it was not noted explicitly in my talk, but actually at the step 1 of the estimation of the regression coefficients beta, we constructed also the estimators for the moments of x to the power of r. So implicitly in this talk it was mentioned, and in addition, we studied the asymptotic normality of the constructed estimators for the regression coefficient beta and variance. And in our future research, we aim to study the following 3 questions. So the first is the asymptotic independence of groups of estimators in order to, in order to make the process of construction of the confidence intervals more effective. It is very convenient to have the asymptotic independence of the groups of estimators in order to and the second is to analyze the proportion in which the classical and Bergson errors affect the quality of the estimation of the regression coefficients beta. This is a very interesting question, which will be also of practical use. And the third is it possible to weaken the conditions and obtain not the strongly consistent estimators, but weakly consistent estimators? So it is not so weak or strong consistency, it doesn't matter for the asymptotic normality. So it is interesting also to study this question. And if someone is interested, you can see the following bibliography. Yes, and thank you for the attention. I would be glad to answer your questions if they arise.
Thank you very much for interesting talk. Maybe someone have questions or comments, please.
And then I want to ask, it seems that to estimate beta, you need not estimate the variance of epsilon.
Yes, that's true.
then what is the reason to estimate the variance of epsilon if it is not a parameter of major interest for us?
But I think that it is important for the practical use in order to probably understand how our regression mod how good is our regression model. So so actually in the radio epidemiology, I think that it is also important to choose the order of the polynomial regression. So probably it may be of great importance to increase the regression the order of regression to reduce the error in the response.
Yes, the first reason is diagnostic
Yes.
of how your model fits the data. But there is another reason that the asymptotic covariance matrix for beta depends on sigma epsilon squared.
Oh,
And
yeah.
to construct the confidence ellipsoid for beta, we need the estimator for sigma epsilon squared. This is the main reason why we do so. Okay, thank you.
Yes, that's also true. Yes, so thank you for the attention.
Okay. If there are no other questions, we have a time to switch to next talk. And our next speaker is Georgy Zelinsky with the talk on two families of random walks on the braid group. Please, Georgy.
Yes, thank you. So today I'll be talking, so in general, thank you for having me on this conference today. So, I think I can share my screen now. Okay. So I would like to thank my scientific advisor, Andrei Anatolyevich Drogovtsov. And today we'll be talking about two families of random walks on the braid group. But firstly, maybe let's talk about what is a braid. So a braid on n strings is an object that consists of two parallel planes in three-dimensional space, and in each of these planes you have a parallel line, and you choose n ordered points on each of these lines, and you join them by these strings called here L1 to Ln, and you add some conditions on them. So specifically, you ask that they have to ascend all the way down, so you cannot have some sort of knot in the middle of the braid. So it looks as shown in the picture. So further, we will project, even though it's a three-dimensional object, we will project it on a plane that passes through these two planes, and we will consider it two-dimensional diagram. So braids, they naturally form the structure of the group. So let me go back. So you can take two braids and compose them. You can put one braid under the other, and you can join the respective nodes. And in the result, you will obtain a new braid. This braid will be called the product of two braids or composition. There is also an inverse. Obviously, you can just under this composition, you can in the second braid you can just switch the crossings to the opposite, and you will obtain the opposite braid. So this geometric braid group consists of braid equivalence classes under ambient isotopy, and the composition is as I described. Also, for further purposes, so the main name the following crossings sigma and sigma to sigma inverse. So it turns out that the braid group can be described algebraically in the following way. So it was well-known theorem by Artin that in fact our group is actually isomorphic to the group that is generated by elements sigma 1 to sigma n and so on. with the following relations. So elements which are not neighboring, they commute, and others, they have this sort of free-term relation in them. And so it will be important to us later also. Also, there is a natural surjective homomorphism from the break group to the symmetric group. So the symmetric group, it has, so how this homomorphism is constructed. So we look at the nodes of this braid, and we look at where they are mapped by the braid. And this mapping, it produces a permutation. So it is surjective, and the kernel of this homomorphism, it's called it is a normal subgroup in a braid group, and we will call it the pure braid group. Also, it is important to note that these braid groups, they are embedded into each other. So if we have one strand, we obtain from braid group on n strands, we obtain on n plus 1. We can take the union of all of them, and we'll form so-called infinite braid group. And analogously, we can consider surjective homomorphism and call the kernel of this homomorphism the pure braid group on infinitely many strands. Okay, let's move on. So we'll further consider two families of random walks on a braid group. In the first one, we'll consider finally generated, so braid group on n strands, and further in the second, we'll consider infinitely generated. So the first one will be obtained in the following way. I'll describe the motivation, why we consider these, what type of questions we will ask, and then I'll introduce them. So firstly, we take, in the first model of the random walk, we'll take essentially random walk on the symmetric group, and then we will lift it to the braid group. So I will talk about it in the next slide, how we do this specifically. And the question that we will ask, since we now have braids, what will be the asymptotic invariance of these braids that are formed in this process? And secondly, when we consider the random walk on an infinite braid group, infinitely generated, we'll ask the question, under what conditions our braids in this process will be of a certain form. So what can we say about them almost surely? Okay, so let's define the first family of random walks. So we'll introduce the following map from group of permutation, the symmetric group, to the braid group. We'll define it in the following way. So we have a permutation. It is well known that any permutation can be represented as a product of transpositions. So these transpositions here are called as Si1 to Sin. And we say that this expression is reduced if it has the smallest possible length, because the product, we can always express it in the following way, but there can be several such expressions. So we'll choose the one with the minimal length. And then we will map these generators respectively. So we map the generators from the symmetric group to the generators of the braid group, sigma I1, sigma IN. So immediately we ask ourselves a question whether this map is actually well defined, because there can be several representations, expressions in the symmetric group which have minimal length. And natural question why this map is even well defined. Well, thankfully we have Matsumoto's theorem which answers these questions. It states that any reduced expressions of the symmetric group, they can be connected of the same permutation, they can be connected by a sequence of braid relations. So these are relations of the form, sorry, yeah, let's go back. These are relations of the following form. And this is why we know that this map is well defined. And then we'll take a random walk on the symmetric group with double stochastic transition probability matrix, so that it has invariant distribution. And we will lift it using this map to the braid group. Now we will obtain the random walk on the braid group in the following. Okay. For our later purposes, especially for the first theorem in this first result that we'll prove, we'll need the concept of Hecke algebras. So let's firstly discuss what is Hecke algebra, and then I'll try to motivate why we introduced that actually. So the Hecke algebra is an algebra with parameter Q, some complex parameter. It is a unital associative C algebra, and it is generated by T1 to Tn minus 1 with the following relations. So we immediately notice that the last two relations are just relations from the Bray group. They look pretty much the same. And we have additionally this quadratic relation. So they naturally arise, Hecke algebras, in the study of representations in the Bray group. So for more algebraic reasons, they are a subject of interest. But here we'll consider them for another purpose. Also, to avoid confusion, I will write, we'll put the Hecke algebra with one generator just to be the polynomial, Laurent polynomial ring with complex coefficients in Q. And we will for convenience, write TV it stands for just the product of generators in the algebra. So these elements differ in basis in the algebra, and we will denote them as follows. If V is reduced in Sn and is a product of Sn, Si1 and so on, Sik. Okay. So we'll also introduce something called Markov trace. So a Markov trace is a certain invariant of braids. It is defined in the following way, which is in a way its own theorem. So it's a theorem construction. There is a unique linear trace called the Markov trace on the infinite Hecke algebra, which satisfies the following relations. So the first relations, they are similar to what we have, just relations of the trace in the linear algebra, the usual trace. And we have one additional relation. So these traces are called Markov traces because there's a theorem in braids, in the study of braids, that's proved by Markov, that two knots, which are obtained as closures of braids, are equivalent if and only if they're invariant under so-called Markov moves. This theorem states that there is, essentially it states that there is a trace, the unique trace, that is invariant under these moves. So that's more or less the motivation behind it. So now we'll prove the following theorem. We'll try to prove it. So let P be the representation of the break group, infinite break group in Hecke algebra, such that they map generators to each other. So we have certain asymptotics on in this theorem, we obtain a certain asymptotics on the Markov trace, which is equal to the following polynomial. So in order to use to prove this theorem, we will need some representation theory of the symmetric group. So firstly, maybe let me remind some well-known facts from representation theory of the symmetric group. So it is well known that for finite groups, there is an irreducible representation. Irreducible representation, they're in one-to-one correspondence with conjugacy classes of the group. And if we take in our example, the symmetric group, then we know that the conjugacy classes in the symmetric group, they correspond to essentially cycle decompositions. And these cycle decompositions, they are defined by partitions of n, and they can be represented by Young diagrams. So these are diagrams that look like this. Which consists of blocks, and number of blocks decreases as we go down. So now the calculation of Markov trace using just relations, it's sometimes a little bit involved and difficult. So we will need the one theorem, which will express this Markov trace in a following, in a way that's as a weighted sum of usual traces in the representations, which we some knowledge of how to compute. Okay, so we'll need the following theorem. So suppose we have some element x in Hecke algebra, and we will denote in the following way the usual trace in Hecke algebra. So usual trace that we linear algebra evaluated for the image of the representation that corresponds to Young diagram. So we know that Young diagrams they correspond to representations, irreducible representations of the symmetric group. And we have the following sort of Fourier transform for groups, essentially. So the sum here is taken of all Young diagrams, and the coefficients here. So the formula, explicit formula for these coefficients is a little bit involved and will not be the point of this presentation, but they are described in a paper by Jones. So yes, the main point is that these coefficients, they can be computed just through the knowing the Young diagram. So it's kind of similar to how you compute Hooke length formulas, but you have additional parameter Q, and it is similar. But before we prove the theorem that I stated above, we will need several lemmas. So the first lemma is quite easy. We just basically linear algebra. So let me quickly go over it. So it states that if we have some projection, then the trace of this projection will be a multiple of the rank. So let's consider the characteristic polynomial. It is separable because alpha is non-zero. Lambda here is non-zero, a complex number. Then we know that this matrix is diagonalizable, and on the diagonal are only zeros and lambdas. And the number of lambdas in this block is just rank, because zeros, they correspond to the kernel, and lambdas, they correspond to the rank. So in this way, we obtain that if you sum these lambdas, then you get the statement of the lambda. Okay, let's go further. We'll need another lemma. It states that if we have the sum of all bases in Hecke algebra, and we square it, then we have the following relation. So it states that H is actually a central projection. So the proof is just some calculations which use we use essentially relations in Hecke algebra. So I'll just quickly go over it because it's not very important. We need the result actually. So as we can see now, so the main idea is to divide this sum as we multiply it into two parts, and each part we can just evaluate using relations of the Hecke algebra. So in this way, we show that HTI is equal to QH, and if we use the following proposition, then we will see that if we multiply it by arbitrary TV, then we'll get the result. So one important point why these two, why we have equality here. So basically, this is because of this proposition, which is just the formula for the generating function of the inversion number in the symmetric group. Okay, now using this lemmas, we can actually prove the theorem, and the theorem is quite easy. The proof is quite easy. So we use the Fourier transform for the Markov trace, and then we can write it in the following way. An important point is that if we look at the action of some endomorphism of this vector space, of this representation, irreducible, then it commutes. So we use here the facts in these equalities that B and H, they are commuting. And from this, we obtain that this this is subrepresentation of this. But since Py is reducible, since we sum over irreducible representations, then it has to be either zero or the full space. But it can be the full space only if the representation is trivial. So the only summand in this sum is just the one that corresponds to the trivial representation. Okay. So Let's compute it. So let y0 be the Young diagram that corresponds trivial representation. And essentially using those formulas that I omitted for the expressions of these weighted coefficients, we can obtain the theorem. So yeah, it's just it's not very difficult, but from this, we can see that the result follows. So we obtain that the sum of all trace of the sum of all elements is equal to this. And now we will use pretty standard results in theory of Markov chains to prove the theorem. So it follows just essentially from the following proposition, which is easily follows from the theory of Markov chains on finite Markov chains. So if we have invariant distribution and we have some, if you have double stochastic matrix, then limiting expectations, they will be given as averages depending on the parity of the elements in the Markov chain. And it follows since in the limits, probabilities in the Markov chain, they will be equal among the classes. So the theorem, this proposition. Okay. And as an example, we can actually try to calculate it for n equal to 3. And see that it's quite easy. Like this sum is just, it can be computed just using trace relations, Hecke algebra relations. Even for larger values of n, it's a bit more difficult. You have a lot more terms, and this is why we need some clever proof to show it for general values of n. Okay. So now we'll go to another another class of random walks. So we will consider finally generated group, and we'll consider a symmetric random walk on it. Yes, so as an example of it, it can be just the standard Polya's random walk on d-dimensional lattice. It is a symmetric random walk. Further, we'll focus on G equal to the Bragg group on n strats. Since it is finally generated, this definition applies. Okay, notice that the Bragg group, it contains a free subgroup which is generated by these two terms. So the idea here is that since it contains a free subgroup, which is, we'll show in this proposition that this random walk on this group is transient, generated by these two terms, then the random walk will be on the Bragg group also transient. So the proof is quite easy. Here we provide a proof for general regular trees because free group on two elements is just for regular tree. Okay. So the proof essentially follows from this bound on the number of paths, which is an easy combinatorics. And then we can bound it by geometric series, which converges for D at least 3. So for 4, it definitely converges. And the random walk is transient by the Laplace theorem. Okay. So to prove the result that I mentioned above, we'll need to introduce about why the random walk on a Bragg group is transient. We'll need to consider the following word metric on the group. So this metric is just equal to the length of the quotients of two elements in the group. We can consider closed balls in this metric. So for example, in Z square, we have, they look as follows in a two-dimensional grid. And the volume of this ball will be given by this formula. So it would be quadratic. So the result that we will need is that the symmetric random walk on a finally generated group is recurrent if and only if this lower limits of volumes is subquadratic. So the the volume grows sub-quadratically. So it works. If it grows faster, then the random walk will be transient. And immediately from this theorem, we get that if G is finally generated, G and N is a subgroup of G, then if it's all okay, maybe let me go back one short moment. So the intuition behind here is that, for example, it is well known that for Polis Volcom, the d-dimensional grid, we know that it is transient if and only if t is at least 3. So this kind of more general result shows that if volumes of the group grows not very fast, not faster than a quadratic term, then it'll be recurrent. Okay, so now let's consider the following random walk on an infinitely generated group. We will consider firstly a symmetric probability measure, which is just so that inverse and measure of elements and its inverse are equal. And we'll consider the following sequence of identically distributed random variables. And we construct a random walk on it just by taking the problem. So random walk on, we'll need the following theorem, which states that if we have a random walk on this union of groups with law mu, then and this chain of finite groups increases, then the criterion for this random walk to be recurrent is that this term is infinite. This term diverges. So the reason why this result will be important to us is because if we take G equal to Sm, then this union will be the finitary, so-called finitary symmetric group. And as we've seen in the beginning, when we talked about braids, that it is related to the pure braid group on infinitely generated braid group. So if we take a sequence of positive reals that sum up to 1, and we let the measure on each generator to be equal to pi, and 0 otherwise, then we have the following theorem that, in fact, this sum, if this sum diverges, if and only if the sum diverges, we know that the random walk on a braid group infinitely generated hits the pure braid group infinitely many times, almost surely. So we know that infinitely often, almost surely, we will have that our braids in this process that we described will be of a certain form. So we will have endpoints will be, so the permutation that acts on its endpoints will be just the identity. So the proof is quite simple, actually. So we just use the result for G is equal to SI in the previous theorem and apply it. And we notice that measure of the symmetric group is just the sum of pi for I less than 1, less than n. And then we see that by the theorem, it's just it will be the sum of tails in this, the tail sum of pi's. Okay, so an important another interpretation of this random process is that we have infinitely many marbles at the beginning of each strand, and each time we multiply by some braid, then these marbles, they interchange. So as we see in this picture, for sigma 1 and sigma 2 inverse, and the interpretation is the following. So we start with infinitely many particles, and then under the conditions that were mentioned in this theorem, we know that this random process will be recurrent. So maybe one more remark that so one might ask why such Pn exists, because they have to, the tail of this sum have to converge to 0 quite quickly. And we can take Pn equal to n to the alpha over n factorial. So asymptotically as this, and they work just some standard calculation. So here we have for alpha less than 1, we know that this series diverges, and hence it is recurrent. Okay, so this is it. Thank you everyone for attention, and if there are any questions, please ask.
Okay, thank you very much for the talk. And maybe someone have questions or comments, please. Actually, we have just time for one small question.
I have a very small question. What would like an example of not recurrent chain on braids?
So you mean in this process, so you mean in infinitely generated braid group, or so here? Whatever it was. In this
because
process,
this interpretation of marbles one, it's kind of natural to expect that they will return to the same configuration. But what should happen for them to lose this recurrency?
Well, I mean, so it is answered in the theorem. So we know that it works in both ways. So if the tails, they don't converge to n factorial quite fast, so quite slowly, then I mean, this process won't be recurrent. It will be transient, actually.
So what does this mean in the terms of configurations? They will like stabilize at some domains, or will fluctuate in some domains, but
so it's quite difficult to say like more precisely. If this condition doesn't hold, can we say anything else about it? But yeah, I think this is, if we, it depends on the probabilities quite, these PIs that we choose. So yeah, I don't think we can say something if we say something if the process is transient. So it's kind of the reason why we consider it recurrence and transience is because actually random walks on infinitely generated groups, they are very difficult to study, because on finitely generated groups you can have very nice theory that essentially uses some. So you can more or less decide if, as I was, I mean, maybe on just like, yeah, so more or less this theorem tells you where, if the process is recurrent or not. And you can say a lot more about finally generated case. Infinitely generated is more difficult. So that's why
I see.
This results, even proving recurrence is not very true.
Thank you.
Okay, I must add that the second part arises from my question: what happened with one particle in this infinite braid? Will this particle go to infinity or not, or it will came back? And I hope we will solve such problems. And for those who are familiar with coalescence processes, this is another opportunity, at least for countable places of start. We can consider such infinite braid, and then, as Nikolai comments, it is interesting to think about configurations and so on. So I hope we will do this. Actually, this is one of our aims. Okay, thank you again. And now, as I told you yesterday, we have extra talk which we move from yesterday's schedule to this, and the talk will be delivered by Chang Wei Qiang, privacy data pricing based on a stackable game approach, please.
Oh, excuse me. I can't
Yes.
share my.
Okay, please do it.
Okay. I can't share my presentation.
Let's try again, maybe.
Hold on, please. Sorry.
Okay, you can proceed as follows. We already face such problems. Please send your presentation right now to Katerina. She will share a screen and you will just say when we have to switch slides.
Okay. Hold on, please.
Please send your presentation to Katerina.
Okay, I will send it.
Did you send the presentation?
Yes, I sent to the.
Okay. Katerina, did you receive presentation?
Do you receive the file?
Sorry again.
Katerina, do you receive the presentation at your email?
No. Can you resend it again?
Okay, I will send it again. Do you receive the email? No.
No.
Hmm? Oh.
You can also try to send it through the chat inside the Zoom.
Okay,
It seems it should work.
Okay.
Or you can write your email address and I'll email you. Maybe. Okay.
Oh,
I send my.
okay, it is in chat.
PowerPoint.
Maybe Katerina, can you open it and demonstrate for us?
Mm-hmm.
Okay, good.
Oh. Why I can't open it?
Oh, now Katerina is doing this, yeah? Okay, so you will just say next slide and Katerina will switch it, okay?
Oh, okay.
So you can start.
Okay, but I can't to the next page.
You will just say when you need next page, then please say Katerina next page and Katerina will switch to the next page, okay?
Okay, thank you very much.
So please start.
Okay. First of all, I want to apologize. My presentation was supposed to be yesterday, but my wife had a sudden illness. I'm very sorry for taking your time. Today, I'm very glad to be here and share my work. The title of my talk is Privacy Data Pricing based on Sternberg game approach. Before I start, I would like to briefly explain why I study privacy data pricing. In the digital world, data is very important. Companies and researchers need data to make better decisions. But at the same time, data may contain personal information. If personal data is used, privacy may be lost. So data owners should get compensation for their privacy loss. This leads to an important question. How should we price privacy data in a fair way? In this talk, I will use a Sternberg game to study this problem. The main idea is to balance three things: the banner's value, the data owner's privacy loss, and the market maker's profit. We need the next page. Hello, we need. Oh, okay. Here is a outline of my work. There are two main parts. The first part is a linear pricing model. The second part is a non-linear pricing model. For each part, I will introduce the model, the game framework, and the main results. Because of time, I will not give all proof details. I will merely focus on the basic ideas and the final results. Okay, next page. Now let us start with the first part. This part is about the linear pricing model. In this model, the price has a simple form. It is easy to understand and give us a clear benchmark. This part also helps us see the basic relation between privacy loss, data value, and the price. Okay, the next page. Thank you. This slide shows the trending flow. There are three main roles in this market. The first role is the data owner. The data owner provides privacy data. The second role is the market maker. The market maker collects the data, answers the query, sets the price, and pays compensation. The third role is the banner. The banner sends the banner sends a query and pays for the noise and pays for the noisy answer. The answer contains noise because we need to protect our privacy. At the same time, the market maker must compensate the data owners. The key question is how to set a proper price. Okay, the next page. Okay, on this slide, I introduced three basic conceptions. The first one is linear query. The linear query is a vector queue. For the database X, the query answer is a inner product of Q and X. The second conception is pricing and purchase. The banner asks the query Q and pays the price. Here, sigma is a variance of the noise. The second concept is compensation. The market maker pays each data owner a micro payment. This payment is used to compensate the privacy loss. We use the Laplace machine. The banner don't receive the true answer directly. Instead, the banner receives the true answer plus Laplace noise. This noise practice privacy, but it also reduces the value of the answer. Okay, the next page. Now we define the banner utility. The banner utility is in fact, the banner utility is a value of information measures the price. The value of information means how much benefit the banners get from the noise answer. If the answer is more precise, if the no answer is more precise, the banner gets more value. In this model, a smaller variance sigma means the more privacy answer. So the banner prefers a smaller sigma, but the smaller sigma usually means the higher price. Therefore, the banner must choose a suitable precision level. The banner wants to maximize his own utility. Okay, the next page. Thank you. Wait. Okay, thank you. Next, we define the market maker utility. The market maker utility is a price received from the banner. Measures the total compensation paid to data owners. Each data owner receives a micro payment. This micro payment is related to privacy loss. If the query causes more privacy loss, the data owner should receive more compensation. The market maker earns positive profit only when the banner's payment covers all micro payments. This condition is called the balance. This condition is called the balanced pricing condition. It ensures that the market maker doesn't lose money. Okay, the next page. Thank you. Okay. Now we introduce the no arbitrage condition. The banner. The idea is simple. The banner should not be able to get the same query answer more cheaply by buying several other queries. If one query can be answered by a sequence of other queries, then its price should not be higher than the total price of these queries. This condition makes the price rule is consistent. It also prevents unfair trading. So in our model, the pricing function should be arbitrage free. Okay, the next page. Okay. Now we introduce the pricing function. the market maker tries a pricing parameter key. The basic price is given by k times f squared of q divided by sigma. Here FQ measures the size of the query. The parameter sigma is a noise variance. When sigma is smaller, the answer is more accurate. So the price should be here. Here. The final price is maximum of 2 parts. The first part is a basic price. The second part is a total micro payment. This form keeps the non-arbitrage property and satisfies the balanced pricing condition. Okay, the next page. Thank you. Okay, now we give the form of the micropayments. The micropayments is based on privacy laws. We use the results of different privacy. The privacy laws of each data owner can be bounded by the sensitivity of the query and the noise level. If the query is more sensitive to one person's data, then this person has a large privacy noise. So this person should receive the higher payment. Here, the CI. CI is a privacy cost coefficient of the data owner's of the data owner I. It measures how sensitive this owner is to privacy laws. The micro payments also depends on the query weight and the variance sigma. The smaller sigma gives less noise, so it causes more. So it causes more privacy noise. Okay. Now we need the next page. Thank you. Okay. Now we define the value of information. The balance value is given by AQ divided by the square root of sigma. Here, AQ is a value intensity of the query. It measures how important the query is to the banner. If AQ is large, then the banner value this query is more. Also, if sigma is small, the answer is more privacy. So the value of information is larger. This value function captures the banners need more precision. Okay, next page. Okay. Now we build the Sternberg game. There are 2 stages. In stage 1, the market maker is a leader. The market maker first chooses the pricing parameter key. The goal of the market maker is to maximize its own utility. Okay, the next page. Oh, okay. The stage 2, the banner is a follower. After observing the price room, the banner chooses the various sigma. The banner wants to maximize his own utility. So the market maker moves first, and the banner responds later. This is why we use Sternberg game. Okay, the next page. Okay, thank you. Oh, okay. This slide gives my results of linear pricing model. Due to time, I will not go through the proof here. I will only explain the meaning of the result. The result depends on the relation between AQ of gamma Q. Here, AQ measures the banner's value intensity, and the gamma Q measures the privacy compensation level. There are three keys. First, if AQ is larger than or equal to gamma Q, the banner value is the data is higher. In this case, trade happens and the market maker can get positive profit. Secondly, if the AQ is between gamma Q and 2 gamma Q, the banner's value is in the middle range. In this case, the market maker's utility is 0 always. The price can cover the compensation, but the market maker can't earn extra profit. Third, if AQ is smaller than gamma Q, the banner's value is too low, so the banner doesn't want to buy the data. So the optimal variance is infinity. This means no chance happens. So the main message of 01 is clear. The data trade can be happen only when the banner's value is large enough compared with the privacy compensation cost. Okay, the next page. Thank you. Okay, the next page. I will next. Until to the non-linear freedom. Next, go on. Okay. Now the next page. Now we move to the second part. This part is about non-linear pricing model. The pricing model is simple and useful, but in the real markets, the price may not always be linear. For example, the price may grow more slowly when the basic price becomes large. So we introduce the non-linear pricing function. This makes the model more general. Okay. Under this association, okay, we need the next page. In the non-linear model, the price is given by the G of pair 0. Here, pair 0 is the original basic price. The function G changes the pi into the non-linear price. We assume the G is increasing and concave. Increasing means that the higher basic price gives a higher finite price. Okay, this is reasonable in many markets. We also define the function h of x. The inverse function of h will help us solve the banner's optimal choice. Okay, this lead gives a lemma 2. The lemma says that under our association, the non-linear pricing function is still arbitrage free. The key point is the function G is a sub additive. Sub additive means that the price of two parts together is not larger than the sum of the two spiritual prices. This property comes from the cavity of G. Okay, due to time, I will not present the detail of proof. The important conclusion is the nonlinear price keeps the no arbitrage property. So the nonlinear model is still consistent. Okay, we need the next page. Okay, we need to go on the next page. Okay. Now we build the Sternberg game for the nonlinear model. The game structure is the same as before. In stage 1, the market maker chooses the pricing parameter K, and in stage 2, the banner observes the price rule and chooses the velocity sigma. The banner wants to maximize the value of information minus the nonlinear price. The only difference from the linear model is the pricing function. No, the price is G of K times FQ squared of Q divided by sigma. This makes the analysis more complex, but the economic means is the same. Okay, the next page. Go on. Okay. Firstly, we need okay. So okay, this slide gives the solution of the stage 1. Again, due to time, I will not go through all details proof. I will only explain the main idea. Okay, we need the next page. Go up. Okay. After solving the balance problem and the leaders problem, finally we get the main results. This leader gives the expression for the optimal pricing parameter K star. After substituting the term, we obtain the optimal condition. When AQ is larger than the two gamma Q, we get the K star. This means if the value of the information for banner bigger than 2 gamma Q, the trade is always happen, and the banner and the market maker can choose the K star to be a pricing function. Okay. We need to set. Okay. This leader gives the final Sternberg equilibration for a nonlinear pricing model. This includes two parts. The first part is a balance optimal various sigma star. The second time is a market matrix optimal pricing parameter K star. If the balanced pricing condition holds, then the banner purchases the data. If the condition doesn't hold, then the banner chooses infinite variance. This means the banner doesn't purchase the data. So the finally conclusion is similar to the linear case. The successful privacy data market needs a balance among three factors. The first factor is balance data value, and the second factor is the data owner's privacy laws. Finally, the third factor is the platform's profit. The Sternberg games give us a clear way to describe this balance. Okay, the next page. Hello. I need the next page. The next page. Oh, okay.
Sorry, I guess it's the last one.
Oh.
33 out of 33.
Okay. Thank you. That is all my. That is all for my presentation. Thank you.
Okay, thank you very much. Finally, we got your presentation. And maybe someone have questions or comments, please. Does anybody have questions?
Actually, I have one here related to this theorem. Okay, in this intermediate regime, so we have that gamma of q less than aq less than 2 gamma of q. And the theorem states that for every k, here we have any k greater than 0, and the optimal decision variable, okay, states that every k is optimal. Yeah, am I right? Because the market makers utilities like identically 0. Does this imply that this equilibrium is not unique? Because if so, how should one select among this infinitely many equilibria? Because I think in this this is the reason why it can be economically meaningful in this case.
Okay. If the AQ is smaller than gamma Q, in fact, no trade happen. So K can be the any number. So
Yes, but this ununiqueness essential for the predictive power, because in this game theoretical model, because if every k is optimal, then model doesn't tell us which pricing rule the market maker will actually choose. Am I right? Because also different values of k may lead to the different buyer response and different level of this noise. So here.
yes, because in this case, the banner doesn't buy the data, so the market maker don't choose the key because the trading is no happen.
I think even though there are multiple equilibria, it doesn't matter in the terms of actual actions. They do not happen, simply. So there is no need to choose anything other than do not react to the market.
I think it's practical questionable, actually.
I don't know, just commenting on the slide.
Yeah, thank you.
Okay, maybe we can postpone this discussion. And Thank you again for the talk, and this is the last talk at our conference this year. I wish all participants and members of our audience to be successful. Have a great summer, and hope to see everybody at our Maleven Calculus seminar in the next semester from the beginning of the September. For today, that's all. Bye.
Thank you. Bye.
Bye.